we last left off talking about empirical formula. We learned about Avogadro's number, we learned about the mole, we learned about molar mass, and percent by mass. Percent by mass being of the total mass, how much is each individual element contributing. If we look at the ratio of each atom to atom, we can break it down into the simplest whole number ratio comparison, and that gives us the empirical formula. And that's going to relate to the molecular formula. The molecular formula was I put together all the molecules, and this is how many atoms per compound. Empirical formula was the simplest whole number ratio of those. The example we gave was glucose being C6H12O6. We could simplify that ratio to be a 1 to 2 to 1 of carbon to hydrogen to oxygen. So how do we go about actually determining this? Come on. Okay. So we could approach this from one of three places. But no matter where we start, we just continue along the path of each of these until we get till. So we could either start right next to where we need to be or farthest from it. But either way, it's still the same path. We want, in order to get the empirical formula, we're going to have to compare moles to moles. We can never compare mass to mass because each element weighs different. But when we're comparing moles to moles, we're essentially comparing atom A to atom B. And since each atom is just an atom, we can compare there's 5 atoms of A for every 10 atoms of B. It's like I could say how many girls are in here versus how many boys are in here. If I compared the weight of the girls to the weight of the boys, it would be a different story because we have some people are football players, some people are track and field, some people aren't in any sports, and so the weight is going to fluctuate both by sex and if you're in sports or not. But if we could just compare straight up students to students, we can get a direct determination. So we could start from percent by mass. If we get percent by mass, we're essentially, what are we going to use? We're going to find from percent by mass to find how much mass of each compound do we have. From there, each mass, we can turn that into moles by using the molar mass of each compound. Once we're in the moles, we are going to compare just the simple ratio of moles of A to moles of B. And that will give us our empirical formula, just a simple whole number ratio. We will be looking at this in lab while we try to oxidize magnesium. We're going to burn magnesium in air, and we're going to find how much oxygen binds to how much magnesium. If you know the name magnesium oxide, you should be able to predict what it is. But we're going to pretend we don't know what's the empirical formula and actually test for that by weighing the magnesium before, heating it, hopefully to complete combustion. Part of the problem is people don't always get it to complete combustion. And then finally, weighing it afterwards, and we'll determine how much oxygen is added. And from there, we can find what is the empirical formula of magnesium oxide. But okay, the best way to do this is to actually just look at the practice, do some practice. So a starting problem, we start from the easiest possible position. We have a sample of copper and oxygen. This one we can't tell right off the bat because copper could be copper 1, copper could be copper 2. We don't know without actually looking at the empirical formula. But given that we have 0.853 moles of copper and 0.4265 moles of oxygen, what is the empirical formula? Looking at that, we have moles and moles. So what are we doing? We are just going to compare the two. We're going to find the simplest whole number ratio. So copper to oxygen is going to be 0.853 divided by 0.4265. Now, not everyone is a genius at math, but hopefully you can see, well, even without doing the math, that looks to be about a 2-to-1 ratio, just the 8 to 4. So if you do that math, you actually get, yes, that is a 2-to-1 ratio. If oxygen is 1, that guy's got to be 2. You divide that and you get a 2. So our empirical formula says we have Cu2O1. Now, whether there's actually more copper and more oxygen in the molecular formula, that's to be determined. But most ionic structures, we stick with just the empirical formula. So it's not a big deal either way. Just go for my own accord. Looking at question number 2. Sample of iron and chlorine contained 31.83 grams of iron and 60.62 grams of chlorine. Of Cl2, well, no, the chlorine, it doesn't really matter. So let me quick write that down on the board before I switch to a smaller. And while you may say, well, 31.83, and then 60.62 grams Cl. So if you just compared it directly based on mass alone, you said, well, it's a 1-to-2 ratio. It looks like it's a 1-to-2 ratio, but we cannot compare based on grams alone. What we have to do is we have to turn them into moles. So here's where we have to use the molar mass. Iron, we look at the periodic table, is approximately 55.85 grams per mole. And chlorine is 35.45 grams per mole. So what am I going to do? I'm going to take my grams and turn them into moles. So here's where we have to use our dimensional analysis. So if this is grams, I want to divide by grams, multiply by moles. Grams per 1 mole. So what's 31.8 divided by 55.8? So doing that math real quick. 0.85. I get 0.5699. 5699. That's moles of iron. Doing the same thing with chlorine. 60.62 divided by 35.45 grams per mole. 60.62 gives me 1.710 moles. Now we have a completely different ratio. 1.710 is chlorine, and iron is 0.5699. Now, to find the simplest whole number ratio, we always want to divide by the little one. So for chlorine to iron, we're going to say 1.710 divided by 0.5699. 5699. And we get approximately 3.001. So for all intents and purposes, we get 3. So instead of having a 2-to-1 ratio, which it looked like by mass, we actually have a 3-to-1 ratio. So the actual empirical formula is Fe1Cl3. What do? We turn grams to moles and then compare the whole number ratio. That's exactly what you'll do in lab when we look at the magnesium oxide lab. We will weigh out the magnesium, weigh out the magnesium oxide, subtract out the magnesium to get the oxygen added. Turn grams of both into moles. Look at the simplest whole number ratio. Exactly what we'll be doing in lab. Okay, I think we're back. So one more practice. This one is how we go. What is the empirical formula of a 100-gram compound with, if we had a percentage? So when you have a percentage, you don't actually have to know what is the weight of the compound. Because if you have a percentage, this may trip a couple people up, but you can always assume it's 100 grams. Because you have to undo the percentage. So no matter what, we have the same ratio of masses. 100 grams is the easy way to do it. But if you had 200 grams, what would change? Well, every mass would be doubled. If I had 300 grams, every mass would be tripled. But the easiest way to do this is, so 23.5% oxygen, 70.6% carbon, 5.9% hydrogen. If I multiply all those by 100, 23.5 goes to 23.5 grams of O. 70.6% times 100 divided by 100, because you have to undo the percentage, gets us to 70.6 grams of carbon and 5.9% hydrogen. Going to give us 5.9 grams of hydrogen. So percentages don't really add an extra difficulty to it. As long as you remember, you can turn percentages into grams by multiplying by 100, and it just keeps the same ratio. You don't have to worry about percentages at all. And now we're at the exact same point. The only difference this time is we have 3 elements, but you just do the same exact steps with all 3 elements. Oxygen is 16 grams per 1 mole. Carbon is 12 grams per 1 mole. Hydrogen is about 1 gram per 1 mole. Technically, because this sometimes matters, I'm going to go 1.0, is it 1.007 gram? I don't remember it right off the top of my head, but per 1 mole. So we have to go about and do these conversions. I'm checking the hydrogen real quick. 1.008, yeah. Close enough. So let's look at this. 23.5 divided by 16 equals 1.46. I'm going to keep all the digits for now, but you could probably say 1.47, 70.6 divided by 12 is 5.883. Repeating, you're going to leave it 5.883. And 5.9 divided by 1.007. Oh, wait, I did that. Is 5.859. So that gets them a little bit closer together. Maybe a little bit, I don't know. If I compare carbon to hydrogen, you divide this. It's not exactly 1, but it's 1 to within a rounding error. These guys are essentially the same. The ratio of carbon to hydrogen are essentially the same. But the lowest number is our oxygen. So for every one oxygen, we have how many carbons and how many hydrogens? One x875. So this one I got 3.98, which is approximately 4. If I do that one, that's going to be approximately 4. So our empirical formula is C4H4O1. Because when I look at the whole number ratio, the comparison of carbon to hydrogen to oxygen, for every one oxygen, I have 4 carbon. For every one oxygen, I have 4 hydrogen. For every 4 carbons, we have 4 hydrogens. We have a 1-to-1 direct ratio between the two. That is empirical formula. That's a little bit more complicated of a molecule. Do we know the shape of the molecule? No. Do we know the structure? No. Do we know how everything's connected? No, not from that. But we know what elements make up it and in what ratios. And that's what we're trying to determine. Now, the last step, if this is asked of you, is determining the molecular formula. The first thing to note is that if your mole ratio is not close to a whole number, so 3.98 is pretty close to 4. That's within a rounding error of 4. But if you got a mole ratio of 1.5 to 1, that's not close to 2. It's not really close to 1. Rounding rules say round up to 2. But 1.5 is not really close to 1 or 2. If I got 1.33 repeating to 1, that's not really close to a whole number. Sometimes when you get that, that is because you actually have a improper, essentially you have a 3-to-2 ratio or a 4-to-3 ratio. So be careful. If you get a 1.5 to 1, that's the type of ratio you would get if you had Fe2O3. If you looked at the amount of iron to the amount of oxygen, you would get a 1.5 to 1. So be careful. Don't just round willy-nilly. Sometimes there is a small amount of error that will go in if you do using real data. If you got 1.1 to 1 ratio, that's maybe within reason. A, say, 4.1 9-to-1 ratio, you can maybe, I can maybe round that up to 5. But if it's like 1.75 to 1, it's getting a little bit farther away. That might be an actual fraction. But from there, once we have the empirical formula, if we know the molar mass of the compound, we can determine the molecular formula. Because the empirical formula is essentially one formula unit. It's one fraction of the mass. If we can determine how many formula units would fit into the molecular formula, we can determine what is the molecular formula. So oxalic acid would have an empirical formula of H1C1O2, and it has a molar mass of 90. So what you have to do is first calculate the weight of the empirical formula and determine how many times it goes into the molecular formula. In the case of H1C1O2, 1H is 1. 1 carbon is 12. 2 oxygens are 16 plus 16, so 32. So 32 plus 12 is 44, plus 1 is 45. How many times does 45 go into 90? Well, hopefully you know your doubles, and 45 times 2 is 90. So the empirical formula would be double the molecular formula would be double the empirical formula. So C, it would be H2C2O4. Looking at the problem we just did, C4H4O, how much would this weigh? If I calculate the molar mass of that, 12 times 4 plus 1 times 4 plus 16. 12 times 4, 24, 48. Plus 4 plus 16, that's 20. So the empirical formula's molar mass of C4H4O is 68. If I gave you the molar mass of that as 68, how many times does 68 go into 68? It would be 1. So the empirical formula and molecular formula are the same. If I gave you the molar mass of the compound was 136, you go 136 divided by 68 is 2. So you'd multiply the whole thing by 2. If I did it like 136, like 204, you'd say 68 goes into 204 3 times, and you'd multiply that whole thing by 3. No matter what, your empirical formula should evenly divide into your molecular formula. If you've done it right, they should always be an even perfect division. So if I made this C4H5O, that would be 69. 69 would not divide into 136. And so you would know, oh, I have one too many. But so I don't even have a practice, but I will make up a practice right now. So, but that is the last slide for this chapter. I'm not going to hit on molecular formula too hard. It's the last little bit. If you can do empirical formula, that's 90% of the way there. But let's say I'm thinking. Shoot. I got to work on this in my head real quick. So glycerol is what I'm going to do. Three times 2, 4, 6, 8. Okay. So glycerol, I'm writing. Glycerol has a molecular molar mass of, let's see, 1 plus 12 times 6. Has a molar mass of 92 grams per mole. And it's, let's see, it's 8.69 grams hydrogen. Maybe not the best example, but let's see. Divide 39.13 grams carbon, and the rest would be oxygen. So times 3, 52.17 grams oxygen. So mind you, this is made up spur of the moment. So it's not exactly the best problem. But so what is the empirical formula? What is the molecular formula? So step 1, turn this into moles. 1 gram, 1 mole. You're going to get, well, 8.69 moles of hydrogen. 39 divided by 12 grams, 1 mole. Well, 3.26 moles carbon, and 52.17 divided by 16 grams per 1 mole of oxygen. 0.17 divided by 16. 3.26 moles of oxygen. Okay. Right off the bat, without looking any further, what can we say about the carbon to oxygen ratio? All of you say, well, whatever we have a 1-to-1 ratio of carbon to oxygen. So whatever we have, carbon 1, O 1, H, we don't know yet. So 8.69 divided by 3.26 is, we do this ratio, it's not a nice number. You get 2.665644 something, something, something. One thing we don't have is a nice whole number. I'm going to round it to 2.66. But that is not a whole number. I should not round it like it's a whole number. Does anyone recognize a fraction that it's close to? Yeah, it is close to 2/3. So much so, if I multiplied everything by 3, I would get C3H8O3. C3H8O3. Though we could check it from this number as well. But what is the molar mass of that? 3 times 12 plus 8 plus 3 times 16, it's 92. So what is the empirical formula? C38H03. What is the molecular formula? C38H03. They happen to be the same. They happen to be the same. But you could check it from this spot. 1 times 12 is 12. 1 times 16 is 16. 1 times 2.6 is 2.6, so 30.66. If I divide 92 by 30.66, I would get that ratio of 3. The ratio of 3, that would get us there. It's technically 3.0006, but that is pretty damn close to 3. But okay, so that's just an example made up off the top of my head. Once again, not the best example because the empirical formula and the molecular formula are the same. But it's a good way to check. Did I do this right? Is it the right ratio? Well, does the empirical formula match the molecular formula? Or is the empirical formula evenly divisible by the molecular formula? Yes. Then we've done it right. Done it right. Okay. Now, once again, since I was running so dang far behind, I didn't really think of some of these things in beforehand. Okay, close that out. So, start looking at the old test. I just uploaded this, literally before you got here. Well, most of you were actually here waiting while I was doing it. But this is the old test that we did last year. So let's look at this, and we'll look at this again on Tuesday. So some of these are multiple choice. Some of these are fill in the blank. Obviously, we'll have to take each one as they are. Okay. So I'll read these off. But okay, yeah, before I do this, I'll show you what the very end of this looks like. Scroll down. So some of these are naming, some of these are but at the very end, you always get a periodic table. And I've actually added more useful information onto this one. But there's examples of some of the useful information I gave. Some conversions of like how many miles. Conversions, quick reminder of the metric system, the order of the metric system. I don't give you the factors, but you have to remember, well, kilo, there's 1,000 meters in a kilometer. There's 1,000 millimeters in a meter. There's 1,000 micrometers in a millimeter, and so on and so forth. If you remember that factor of 1,000 to jump there, you're not going to get tripped up on, does it micrometer then nanometer or nanometer then micrometer? Because I got that. And I'll have all the relevant metric to English conversions, because ideally you don't just have it all memorized. Man, my glasses are fogging like so. Well, let's look at these, which there's an easier way to project it both so I can see it for both groups. But okay, the first one is liquid nitrogen freezes at negative 320 degrees Fahrenheit. What is this temperature in Kelvin? So this one's actually harder than the one on the test because this involves two conversions, not just one, but 3 Fahrenheit to Kelvin. So we're going to break down. We want to go from Fahrenheit to Celsius to Kelvin. And I do believe on the useful information, I have that conversion. If I don't, it's on this test. But Fahrenheit to Kelvin. So Fahrenheit is Fahrenheit minus 32 times 5/9. That gives us to Celsius. So if my freezing point is negative 320, make sure to keep the signs. Negative 320.44 minus 32 times 5 divided by 9. And you should get what temperature in Celsius is that? That should be negative 195. So that's the first step. That gets us to Celsius, negative 195.8. Negative 195.8. Finally, to get this into Kelvin, we have to add 273. Celsius plus 273 gives us Kelvin. Because Kelvin can never go below 0. We cannot have a negative temperature in Kelvin. So when we add 273.15, that will give us our Kelvin, which is going to be what, like 78, something like that. And hopefully you'll see that is option A. Option A, 77. Considering I was doing that more or less the second part without a calculator. Question 2 is a lab-based question. Actually, question 2 and question 3. Similar to what we did in lab, a scientist determined the volume delivered by a pipette by dividing the density of water, by dividing the mass by the density of water. They determined the weight of the empty beaker to be 24.316. After pipetting the water into it, the beaker weighed 29.376. So the correct number is sig figs. What is the mass of water delivered? And then to the correct number sig figs, what is the volume of water delivered? So this is a practical sig fig problem. Practical sig fig problem. So when we add and subtract sig figs, we line them up, and then we leave the position. So the 29.376, we have 24.316, and we subtract. So the mass of water, 5.060. Now here's the key thing. Just because that is 0 does not mean we lose that sig fig, because we lined them up here. Just because that's 0 doesn't mean we lose that sig fig. That's a 0 that we know is a 0. So don't leave that out. So we should have 4 sig figs in our answer. Now, that would be question 2. Question 3 then becomes, what is the density? So what is the volume? So I'm dividing by the mass, which is the density, which is 0.9970470. 99. Oh, sorry, 70470. So this one you had to know, read the question, solve the math. This one's much more than 4 sig figs, But what answer should you record this to? You should record this to 4 sig figs, because you always keep the lesser amount of sig figs. All right. 060 divided by 0.99747. So it doesn't change by much, but it goes to 5.075. And that's 4 sig figs. That's 4 sig figs. That's the volume of water we would have delivered. And so that's what I was looking for this problem. Do you remember the simple rules of sig figs, not going too complex? But in this case, everything had a decimal. So simple addition, subtraction in reference to lab. Number 4. We'll finish with number 4 to finish off page 1. Come Wednesday, we will look at page 2 and hopefully most of the rest of it. What are the properties? Which of these properties are not present in all metals? High boiling point, strong thermal conductivity, strong electrical conductivity, strong magnetic attraction. So that one's a little hard, but hopefully you remember almost all metals have a pretty high melting point. All of them conduct electricity. All of them conduct heat really well. The only thing that's not necessarily present is magnetism. There is a lot of magnetism in metals. There's a lot of magnetic metals, but not all metals are necessarily magnetic. So metals are shiny. They're malleable. They have a high melting point, high boiling point. All of them are solid except for mercury. But that's where we'll stop for today. So I bid you adieu.